Greetings, everybody. My name is Kevin Kotchek. I'm the founder CEO of Chemical Q Device here for discussion 81. This is May 4th, 2023. So we're going to be talking about basically 4 quantum machine learning platforms. So we got more people coming in here. These would be, so it's not just IBM Qiskit, but it's IBM Qiskit QML, or quantum machine learning. There's Google TensorFlow Quantum, MIT TorchQuantum, Xanadu Pennylane. So the first to the bunch was Xanadu Pennylane. So you'll see it referenced in a lot of papers. I've worked off of 2 of their models, and it's typically very user-friendly. It has to do with the authors, but basically hyperparameters, changing quantum circuits. So as more people come on here, interested to see where everybody's kind of coming from. We have some people returning, some people familiar faces here as well too. And where you are in QML. So this is quantum machine learning, and basically what you want to get out of it. Moving forward, if you're coming from something like a TensorFlow, which is from Google, and now you're seeing the update with TensorFlow Quantum, or if you're coming something from Torch or PyTorch, and then you're going into TorchQuantum. So be interested to see as far as backgrounds. Some people use these regular machine learning workflows every single day, and you should be able to unmute yourself, or you can come on as well. You could also post in the chat, and then if it's in the form of question, answer it. And there's other people here too that have, definitely, been on the discussion before too as well. So as far as news, it's still a lot of simulators that you'll see in papers, and that's fine. I mean, they're lower qubits and they're helping other machine learning networks. But, the transition will eventually someday go into more of like a more quantum-based code with the machine learning part of it. So that phrase quantum machine learning is typically quantum's there and it's assisting the classical neural network. That's typically most of the code. But you could do things with quantum kernels and, classifications, with quantum as well. So has anybody had experience with either of these 4? So again, there's Qiskit, there's TensorFlow Quantum or TFQ, there's TorchQuantum, there's Pennylane. If you haven't, I would definitely suggest getting on a demo, especially like a Pennylane demo. Qiskit QML has demos, and TensorFlow Quantum has demos as well. So TorchQuantum, it's a little bit early to the game, and I've had some issues with uploading some of the notebooks, but they've had some big papers that have used TorchQuantum there too. Go ahead, Tim, if you have something. And then if not, just is there anything, in specific that you, as far as questions, and this could go all the way down to, I'm not too strong in quantum physics, but more so in programming, the gate level, with quantum circuits, how that gets incorporated with quantum machine learning. Most of the code you'll find is, I just had an MVP, or minimum viable product, yesterday, and it's basically a for loop. And it iterates based on the number of qubits that you have, or the number of qubits that you set in the circuit. So it's a little bit different because it's for I and J and those types of things. But, that specific code, which is quantum transfer learning, it's meant to be more user-friendly. Okay, so we have a question here. So time series, QML approaches plus example, can you give some pointers if I want to start? Could you be just a little bit more specific? Time series QML? And then other people, time series forecast. I guess I'm not too familiar with this, actually. Prediction. I mean, I've worked on several notebooks, but it's mostly prediction of saying like the QML is predicting that your image is going to be this. And then your accuracy is based on whether that prediction was true or not based on your test set. But I'm not too familiar with the time series forecasting and prediction per se. And feel free, you can come on. So you can come on, or you can unmute, with these 2. We have some definitely returning guests here. Tim or Ron, go ahead. And I think even Brian, you can go on as well too.
So I think that this question is related to like perhaps LSTM models, like long-term, short-term memory models being implemented with or simulated through like the one of the tools like Quantum Torch or TensorFlow Quantum, something like that.
Yeah, it's just something I haven't touched on too much. It's not familiar to me. So the time series forecasting, I would definitely say check on each of these individual formats, for more information. That sounds like a Qiskit thing. So Qiskit has for sure one of the best, if not the best, as far as resources, and especially bringing things over from ML or machine learning.
So a time series machine learning classical example is data that comes and it comes consistently and it's keyed to time. So things like temperature, things like data streams that might give you some data that you could potentially predict future weather patterns. Another one would be the stock market. Everybody's familiar with the ticker. Stock prices come off the ticker all the time. That's time sensitive data. So it comes in as a time series. As far as quantum ML for time series, I have heard of, I haven't looked into yet, that especially in the financial market, there are people who want to take a look at that. Classical machine learning hasn't, as far as I know, done that much for predicting the stock market based just off of the stock prices themselves. They tend to also incorporate other streams of data or other facts of data, like the world environment and that sort of thing. But there probably would be a possibility that quantum could speed that up, or it actually would. They don't need it to speed it up. What they need is to get it to be more accurate in the predictions.
Okay. Yeah, I mean, what comes off the top of my head is basically for quantum simulators, they're basically slower, I believe, than if you're running classical data off of CPUs, because you're doing things quantum mechanically. And the advantage with that is it's completely error-free compared to real quantum computers, which would have that speed advantage, right? So simulators would go more towards accuracy, and then speed would go towards a real quantum computer. So, I mean, like as Ron said, if the thing is more accuracy, then smaller quantum circuits have been used in medical and images and these types of things several times, for improved accuracy. And as long as it's not too complex, it's not going to slow things down to a great extent. And that gets into, so this field is called variational quantum circuits, or I refer to it as parameterized quantum circuits. And it's also being used for cybersecurity because you don't need a quantum computer to defend. You're just running a quantum algorithm on a quantum simulator as if something happens to your computer in the US. I believe we had some other people come on, and then some other people that familiar with too. So Antonio, let's see, or Frank, go on. So I definitely attended some of these other series too in high tech, and I appreciate those, coming back on. So it's good to see everybody there. And yeah, so Antonio or Frank.
Hey, so I'm excited to be here and catch up on the latest happenings in quantum. I've been stuck in ChatGPT land, so kind of knee deep in that, but I can always ask ChatGPT to explain quantum computers.
Yeah, I appreciate that. And actually, if you go to ChatGPT's home site, where you go to start coding or start asking questions, I should say, it'll say that, the first question is, what is a quantum computer, or how does a quantum computer work? So yeah, it'd be interesting because as I was just sharing, Frank, and this goes for everybody too, is that right now the key is these smaller quantum circuits that are assisting classical neural networks, like a convolutional neural network. And I just finished up an MVP, so it's a quantum transfer learning, where it's actually trained off the ImageNet data set. And then you don't need too much additional training data and testing data in order to get pretty good results. So you're going to see that it's basically a supplement as opposed to having a full out. Although if you want to take the challenge, IBM has a demo. So this is a notebook, and it's an 8-qubit, or it's an 8-pixel image, and then that takes 8 qubits to simulate. So if you want to get creative with it, you can simulate up to 40 qubits depending on your account. So maybe like 15 or 20 if you have the free one. But it's interesting because that's the quantum approach. Is it takes a qubit or a quantum bit per pixel in that specific model. So it just really depends on what's trying to be done. Yeah, for quantum speeder for large language models, I appreciate the questions here, Parminder, on natural language processing side. Like I said, I believe, and there's on LinkedIn too, I've seen other people post that quantum will be coming to large language models / GPT, natural language processing. It's only a matter of time. And like I said, it's mostly going to be these smaller quantum circuits, but if there's a breakthrough and there's 5 or 6 different type of hardware technologies out there, that could mean a huge thing, and it's basically would boost their number of parameters significantly. And large language like ChatGPT uses its unsupervised learning and reinforced learning, so it's not supervised. So it can't do everything basically, but that's the train of thought. And that's, especially with that first question on on their site there is, how does a quantum computer work? And by the way, they're funded by Microsoft as I think a couple months ago. Yeah. So I would just, with any of these things, I would just fully investigate it. And there's papers out there too. You're best off in literature. It's better off to read maybe like 1 or 2 papers and fully understand them, as opposed to just mainstream news, right? So a lot of times they summarize something and it doesn't catch the full story, basically.
I had a question.
Yeah, go ahead, Brian.
So nice to meet you, by the way, Kevin. So I'm very interested in what you guys are doing in the medical space with quantum computing. That's really interesting.
So image analysis is doing well as far as other things like drug discovery. And I don't focus really on drug discovery, but the thing with image analysis is there's many different ways of using quantum circuits and technology, all these types of things. And the thing right now is it's called a CQ model. So you have classical data of an image, it goes into quantum, and from quantum it goes into classical. That's 9 out of 10 papers that you're going to find. And we're getting up there in numbers. For brain images, 4 or 5, something like that. So in specific, it's not even close as far as the computational power, the workload that the classical is carrying, like a convolutional neural net, but it's helping it. So say, for instance, like if you have 512 features, it goes down to 4. In this QTL paper, Quantum Transfer Learning by Pennylane, I've been focusing on, those go into the quantum circuit, and then that has 4 qubits. So a lot of times features match qubits, and it just depends. But there's many different ways of going about this as far as getting a better classification accuracy. So I just did a glioma and no tumor. And then I was able to get high classification accuracy. It's only binary, so that's 2. And I think the model, or like the notebook, like what you're coding in, only goes up to 2. But that'll be the next advancements, is more classifications. There's another paper that did 4. So that's three classes of brain tumors and then an additional no tumor. And you can get that data set on Kaggle, Google Kaggle, easily. It's de-identified, it doesn't have patient data. So that's probably a leader right there. And then there's other ones that have done some fully connected neural networks up to 20 qubits. And again, it's like a plug and play kind of thing with where do you choose to use quantum code at?
Thanks for sharing.
And I would say for anybody looking into this, the big jump is basically if you have an MNIST data set that's on Keras, this is TensorFlow, and you're trying to get up to loading your own data, that's a really big jump. So you want to look for a model that you can upload your own data analogous to how they did. It's just your folder names are different, and then, you know, the labels will be different. But I would not go that way. I tried that. Basically, if you have like a conventional neural network and I was trying to insert quantum code, and it just, you know, there's many different places it can go wrong. So like I said, the QTL that I did my MVP based off of, and I optimized parameters, you know, both on quantum and classical, is that worked for me. Okay, so yeah, keep the questions coming for sure. Yeah, there's GitHub examples for sure. Now, of the 4 I listed, so in 2018, Xanadu released Pennylane, and that was the first to the market. And then the second was Google TensorFlow Quantum in 2020. Number 3 was IBM Qiskit with their QML. They had, you know, other non-QML stuff in 2021. And then the last one is MIT TorchQuantum, which I'm going to focus on. It's 2022, and that's available on GitHub. Like I said, I've had some issues with these are .ipnybs files, even opening. And I got them to open up in NBViewer. I think it's nbviewer.org or .com. So I just heard that you repped it. Yeah. So, and I did a lot with MNIST data sets. I did a lot with, this is Pennylane, and I kept updating that model with better accuracy. I also did some IBMs. So these are pure quantum data, but very limited in image size. So the issue is you want, basically you want as much quantum data as possible, but that's an issue because images are classical. So in theory, you're not getting as big of a benefit from going from classical data to quantum data, and then quantum data back to classical, say for like a classification at the end. And on the TorchQuantum side, the paper, I actually came across 3 of these papers. They're scalable quantum convolutional neural nets, if you guys do image analysis. And then I also came across, it's called PVM, versus POVM. POVM is a standard method. I don't know the abbreviation off the top of my head. And I know for sure that most of these are on GitHub, basically. TensorFlow Quantum, you can actually run it straight into Colab with like a click. Colab is like an online Jupyter notebook for coding. Okay. And then so you said you use some examples from Qiskit ML from Iris Wine dataset. Okay. And I'd be interested how those worked out as well. And, you know, from those that we haven't heard from yet, I'd be interested to hear from. So I see a number of new people that have Dinesh or Sean, and then anybody that we haven't heard from previously. And it's just one of those things, is the more you read and the more YouTube videos you watch, the better off you'll be, because you'll get stuck down a rabbit hole, pretty quickly. If you're trying to get a certain type of image data set into something that doesn't like that. And it's saying we want a tuple of lists instead of a list, and it'll get very fundamental on you, like as far as Python goes. And kind of like the corrections it wants you to make with the notebook. And then, so Frank said, so finding the global minimum loss should be ideal for quantum. Yeah, so Frank, there's a thing called tunneling, and then other people have touched on this too in other meetups that we go to. It's called, quantum tunneling. So it's basically getting to the minimum that you want, instead of, going over all these bumps. And the whole goal with all of this that's being discussed is finding the applications that it makes sense to use quantum. So if you were to take a huge chalkboard and then fill up, from left to right, all the different things for your specific area in healthcare. So if it's image analysis, it's something else. And then for each of those, you want to find out, is it possible to get a lot greater performance with quantum simulators or hardware, or is it possible to get a lot better efficiency with simulators or hardware? And then to me, without doing this fully, it sounds like a myriad of applications, and I'm sure there's several or at least many, but it's just, those are the things you want to do, right? Like look at the papers, see what's been done. can you jump up from a binary to like a 4-class classification, on this specific model, or do you have to switch to something else? Is it taking too long to run? There's many cases that just disqualify use for in anything, in any emerging technology, and you want to find the ones that really kind of stand out.
I have a question, Kevin.
Yeah, go ahead.
That may be in your arena. So, what about brain signal analysis with the quantum computing?
You're typically talking like MEG and EEG. EEGs are electrical, MEGs are magnetic. And I've had this discussion with other people, in recent, weeks and months. And basically, that it's surface, right? So an MRI is more like it can see the brain, more of the brain, but the MEG and EEG has other advantages. So if you were going to do something like that, MEG, EEG, MRI, or even PET scan, that sees more inside the brain, you have to figure out, so what part of the quantum can you do now, with quantum simulators that'll help to do, quantum circuit on. And then, what part's going to emerge, for instance. Now, what oftentimes comes up is consciousness. And consciousness, the brain is deep. And like I said, the EEG and MEG can only see an approximation of synapses fired. They don't see single cells firing, basically. So there's technologies that you'll read about in the news that they have that. Basically, single synapse, you can detect these types of things. And I believe it's just located to a specific region. And then, so now you're talking about approximations, because now you have that specific region, and we'll say, we could see this here, and we're going to assume or deduce that this is happening in other parts of the brain. Now, the quantum computer and the ones that you hear about in the news is basically, high qubits, this will open up many parameters, like exponential parameters. The amount of time it will take to process these things are only logarithmic as opposed to exponential with classical. And these things are all theoretically possible, but we've never had a quantum computer that we can fully test because we don't have one. So the algorithms that we have, and I think Grover's search kind of got into some hot water in recent months, that's the other part too. Like, in theory, if the math says it should work, but is there something with the quantum computers that's going to hold it back too? So I would say, have an idea of what you want to aim for in the future, but also be realistic as far as, this is what we can do now. This is what a quantum simulator could help, or even maybe even ion trap, quantum computer could help with now, and plan that into the forecast. But as qubits grow and noise theoretically will decrease, as it has been, like I said, some of these things aren't 100% because we can't test them. We can't test the algorithms because the hardware doesn't exist to do it, unless there's something unpublished that we don't know about.
Thanks, Kevin.
Yeah, and then, I appreciate all the feedback in the chat for sure. And I mean, the greatest benefit you're going to get is listening to other experts talk. I was just listening to some TensorFlow Medical and, PyTorch one, and they'll tell you up front, like, a lot of times, if you have an image, like say in a lab, it's not the issue. The issue isn't the AI. It's just the issue is there's too much light in the room, or like the patient is like trying to dig into their, belongings, and it takes a bad photo. So the solutions for those two were get curtains and get a shelf for your personal belongings in order to get better, eye images or fundus images, basically. So it's the same thing. Like, you really have to think all this through. And for me, do basically more and more interviews to find out exactly what could help bringing in, say, a quantum solution that's not even quantum based, where, quantum would prospectively bring performance and or efficiency benefits. But yeah, it's all about practical use, because a lot of these aren't like Stanford hospitals and, Harvard, leading healthcare systems that you'll have a specific interface on the computer and they want to keep using that. And then you have to basically manipulate your high tech to function with that, a legacy system, basically. And it's a definitely an emerging field. When you go into any emerging technology, you're not well, I shouldn't say all, but I'm not alone. So there's Fermilab. So they're partnering with NYU Langone, and they're building their own quantum computers and quantum systems for MRI analysis. So I think it's more on the hardware side of things. And then, you have Mount Sinai Hospital, and then you also have Cleveland Clinic, that these top hospitals, they just put in a real quantum computer into the Cleveland Clinic in Ohio, and that's by IBM, and they had like 10 people stand up side by side. So I would say that the support and the backing is definitely behind the technology. That specific quantum computer that's in there isn't going to be ready for patient use, likely for years, just because of the noise and in the system. But it's a good, basically putting all of this effort and money behind the technology that a lot of people believe in, that will pan out over time. And probably a lot bigger jump from like a CPU to a GPU, or like and I could be wrong on this, but or like a CPU to a tensor processing unit, because it's using quantum mechanics. It's not zeros and ones, or it's basically 0, 1, or anything in between. It's superpositioned for that quantum bit. Yeah, so I think this is a challenge for everybody else too. So Perminda basically asked, which of the four, to pick one. And I try not to make this a direct head-to-head, even though that's how it looks on the paper, is it really just depends on where you're coming from. A lot of times people, even we don't talk too much about TorchQuantum, is based on PyTorch, and Tesla uses it, and these huge companies use, PyTorch, this machine learning, prior to all this quantum. And I believe that question, and other people could chime in too, as far as where you're coming from, which to pick out of the four. I will tell you this, and I'd like to hear some from other people too. I would definitely start off with IBM Qiskit. Number one, it's free. You can do both, draw your own quantum circuits on Composer. And then I think you can be safe to run up to like a 15 qubit quantum circuits with like 8 gigs of RAM is what they give you. So I would start there. And then for me, I wind up on models, the actual notebooks. And then Pennylane seems to have the ones that are more, user-friendly, and then I can build on over time, and they tend to just run, And I would say if you're a super duper researcher and you want to have your own platform that's based on, TorchQuantum, this is MIT's, that seems to be the one, because you could do stuff as far as not only train the parameters on your quantum circuit, but you could also train the circuit itself in order to put that into your specific code. And then TensorFlow Quantum has that background, right? Like, so they have Google. This is coming from TensorFlow basically, and they have some decent models. One of them they already kind of maxed out on, so I was like, what's the fun in that for me? If they already got 100%, right? But a lot of it just depends on what you've worked on before with machine learning, I would say. And then anybody else that we haven't heard from? So we have a number of people here. So Antonio, Ron, or Perminda, you could unmute or come on. And we're still early in the game with this, and it's good because there's not an awesome book that answers every question. Like there was another question like, which book should I have? It's like, you have to try them out. This is not a fully established field. So go ahead, Ron.
I was going to say that, yeah, if you're just getting started, the IBM Quantum Experience is a great place to start. You can either go into the graphical circuit builder and play around with things, or you can go into the lab and actually write code in either the Qiskit level or the Open Chasm level. Actually, the whole Qiskit thing allows you to manipulate your products at a number of different levels, although I don't recommend going to the deeper levels for the faint of heart. That's where they start messing with, you're actually controlling the laser or the microwave pulses that are being fired at your qubits. Probably leave that to the actual quantum mechanics, but I wanted to mention that I'm going to think that in the very short term, probably this year sometime, IBM will open up their 127-bit chips to the free tier.
Yeah, I think they just had news on that. I just saw.
Yeah, I actually just signed up for it, so see
Okay.
what happens. Yeah.
So that's called Eagle.
Yeah, it's the Eagle chip, and I'm getting the feeling, this is just a gut feeling based on, you know, watching the Qiskit seminars and the news coming from IBM, that they are putting those Eagle wafers into production, that they've got more than just a handful now. So they're going to be able to distribute them to their various cryogenic facilities and get them online. The next one up from Eagle, I believe, is I forget the name. It's another bird name.
Osprey.
Osprey. The Osprey is a 420 cubic thing, but the best I can tell, they've only got 2 of those, and they hasn't gone into production yet. But this information is maybe a few months old, maybe little older, but I haven't heard anything much more about that. They already, though, have published plans to go beyond the Osprey to the pterodactyl, which is like 4 to 5 times the size of the Osprey. And without, again, you know, they're really holding details close to the vest over there at IBM, but I get the feeling that once they tackle the problems that they've been faced with, and get the Osprey online and get it usable, I believe that the next step is they're going to start stacking them on top of each other, so that instead of going with a 2-dimensional array of qubits, they'll have a 3-dimensional array of qubits. Again, this is just based on what I'm gleaning out of what information they do put out. They don't really talk too much about it, but again, important thing is I'm thinking this sometime this year that you'll be able to access. You might be under special circumstances, but they're already telling me that the 2023 Quantum Experience is going to be making these Eagle chips available to the participants. So that probably means they have a bunch of them online and working.
Yeah, it's an interesting thing. If you do it yourself, I use, it's a 7-qubit, and it's good for smaller circuits, which what everything tends to be anyway. It's a Nairobi on IBM Qiskit. It's on basically Composer, and it's good if you start getting deeper in your circuits, or if you start adding more qubits, or it's called getting wider with it, is you'll start to see some of your probabilities start to shift to others. So a lot of circuits, you have a primary probability and you want to keep it there, right? So this is what we're talking about, how it relates to software and QML, is basically if ion trap might be winning, which isn't, you know, IBM's, then and actually they published this as specific circuits up to like 25 qubits, I think Monte Carlo simulations, that it's still blue and it doesn't go to red. And the issue is as things get more complex, is that your chances of error and every single quantum gate. So quantum gate is software. It's a matrix. Every specific matrix operation introduces error to the system, and we're talking real quantum computers here. And I mean, the stuff that's coming up, I mean, Ion Trap says we're getting a manufacturing facility first half of next year. We're still NSF, National Science Foundation, which was the first to fund quantum technologies in the early 1980s. They say we're supposed to get a practical quantum computer this year. And also the IBM stuff, they say by the end of this year, 16,000 plus qubit modular system. And that goes along with what Ron was talking about, the Osprey. And it's just a question of, number one is like, what applications will that be good for? And then number two, if you have a sensitive field like finance or medical, is that okay to have that much error still around? And the error that we're talking about is still 99.99%, like a 2-qubit gate fidelity is what they call it. And it needs to be more like a 99.9999, like, I don't know, 5 or 7 nines, like our phones are, I think, 7 or 9 nines out, 99.99, the list goes on. So yes, unfortunately, all this connects as far as the hardware, the software, because you're limited by the QPU. And then, like I said, you could do a fair amount with smaller quantum circuits on simulators, either GPU or CPU based, but they're slow and they're limited in qubits. So you're not going to see this. You're missing out on some of the purported quantum advantage with things, but at that same time, it's doing it by quantum mechanics math. So that's the advantage even with smaller circuits. So with that, I'd be interested. Okay, so which QML? Oh, okay, so I have to. Okay, you're going to see continual hardware announcements and maybe the neutral atom and spin qubits maybe a little bit later on. That if as things develop, if they're developed, kind of thing. And then the top two, I would say the gate-based superconducting qubit, and then ion trap technology. And my assumption is implementing these, because we had a question, which of these 4 QML platforms to use? And a lot of times it's not a direct answer because they're still relatively early, even though, Pennylane came out in 2018. For me, if it's a name thing in healthcare, something like Pennylane would sound good, right? It's soothing, maybe more than the other ones, but it could come down to how you like to code, because Pennylane is .hadamard instead of .h as with like IBM Qiskit. But these things are splitting hairs, right? So the Qiskit actually has a torch connector that connects into PyTorch. And Qiskit also has their own QML platform, like neural network, and I think 2 estimator QNN, and I think 2 other ones. So so it's a naming game too. And IBM probably has the best roadmap, but I think it gets updated quite frequently. And we're due for some, so we're in the dynamic circuits phase. So dynamic circuits is basically you're implementing more classical into quantum and only doing quantum on the quantum computer where it absolutely has to, and you're getting better results just because of the whole error thing and trying to fix the situation. So, and likewise, so this is TensorFlow quantum uses gate fusion. So if you have like a Hadamard gate and some other gates that are in close proximity, it'll do the matrix multiplication before the quantum comes in to do the the quantum circuit. So it's like a pre-multiplication. And like I said, simulators is being used quite often because the results are good. It's just the applications, you're not going to go very too far with it, even though that's what I'm based on is using simulators too. So I'd like to get, as far as everything that's been said, what's most on your mind as far as like, is it the hardware, the software, only quantum machine learning? Is it machine learning going into QML? These types of things, feel free to put in the chat. And then we haven't heard from a couple people. And so Mohammed, Sean, or Marco, feel free to come in. And, you could just tell us a little story as far as where you're coming from, in machine learning or data science, these types of things too. Go ahead, Sean.
Yeah, I'm very new, but I'm just learning. So it's great to be here and hear what the state of the environment is.
Yeah, appreciate it. So, and don't be bashful. The people that'll make it in QML and quantum, whether it's physics or programming or quantum machine learning, is you just don't give up, right? So by the time it comes mainstream, many more people will be involved. And in my opinion, it's best to get in early, right? It's, I mean, relatively early, as opposed to hearing this and not doing anything for like 2 years. And the time will come that, you know, I believe your average boss will say, oh yeah, do you have any quantum experience? And they'll say, what does that mean? It's like, oh, physics or programming or quantum machine learning, these types of things, TensorFlow quantum, because it's so heavily developed. There's billions of dollars in quantum, either sensing, quantum computing, all this stuff. So it's a good use case is basically NVIDIA. So not only it's called QCUDA, it's the quantum version of their, it's basically running quantum mechanics on a GPU. And then they also have this new thing called DGX, where it's fixing the error of the quantum computer called by Quantum Machines Company with a GPU. And then there's just so much development out there that really anything could break. And I would still kind of plan a lot based on quantum simulators though. So interested in algorithms. Yeah, algorithms are applications. So typically algorithms are small, right? Especially these days. And a lot of times when you're in Qiskit, not only it's hard, well, you have to read lots of papers. So basically on Qiskit, it'll give you state vectors and probabilities, right? Most people just look at probabilities, in my opinion. And then in papers, there's generalization, there's expressibility is a huge one. And then if you're in quantum machine learning, it might be more important to have one of those characteristics than other ones. So Qiskit, like I said, that it doesn't give you all the information, basically, if you're looking for a killer algorithm. Now, keep in mind, machine learning is being used to optimize quantum algorithms. So, you know, there's going to be a fair number of these algorithms that were, you know, done by machine learning, not by human hands or theoretically by human imagination. And the challenge is like with anything, even inserting a data set, right? That can come from many different places, or the errors can come from anywhere. And, you know, moving forward, if you want to be a quantum programmer, you know, it's not quite clear to me exactly what you'll be doing, because like I said, a lot of the machine learning is going to be helping out, you know, either optimize quantum parameters, which it already does today. That's an algorithm. And then it already optimized, or MIT's, like this is TorchQuantum, you can optimize quantum circuits with classical machine learning too. So it's kind of like, I try to relate things as far as like what a future job will look like, you know, using quantum machine learning. And I don't know if anybody else has insight on that, because, you know, this is in an ideal world, right? Ideally, you want everything done by AI. And, you know, as far as the time consuming things, and then you still need the human, it's a human AI team, the human to program it all. Okay, so Mohammed said, I have a background in physics. I have been doing quantum since last August. I am also interested in AI. So naturally, I am quite interested in QML. Awesome. Yeah, and you know, keep in mind, so the TensorFlow quantum and TorchQuantum, a lot of it is just, it's classical. And then in specific places, like with TensorFlow quantum, you're using Google Circ, which is to make algorithms. And then in parts of the code are going quantum. That's just how most, you know, that's how a lot of, like, say, like working code looks like. It's just mostly classical. And by the way, this part does quantum, it runs on a quantum simulator. There you go. And there's more, there's other meetups too. So, and you can get into the physics side, and, you know, this is more programming here that we're talking about. And, you know, with QML, I would definitely say do a bunch of the models. So I did a couple of the IBM, I did a couple Pennylane based, and I ran a TensorFlow quantum, and the other TorchQuantum I had issues with. So you learn a lot more if you're actually, you know, you run something, you know, fix parameters, fix the quantum circuit, those types of things. So it's really, these questions can kind of get broad as far as like the exact thing that you want to do in QML. So Ron says DSLs and the development of the computers, not too familiar. So I'll answer this. So this other one, I'm interested in using ML to figure out new cell types using single cell technology related to cancer. Does QML help? Okay, so I'll give you the ideal world answer first with that. Is in the ideal world, QML can do exponential amount of data, but the quantum computer can't. So the QPU is doing a specific task while the classical is. And the closest thing I have for you is basically there's at least 9 or 10 startups, if not even Johnson & Johnson is into this too, or Janssen Pharmaceuticals, and they're doing drug discovery. And say, for instance, if you have molecules, which are smaller than cells, then you can't look at them in 3D and you have to flatten them. And then you have to approximate, say, for instance, the problem that you're trying to solve, because it quickly becomes, you know, very computationally heavy, and we're not quite there with the computers. So when you say single cell technology related to cancer, it just depends. Like, are you just counting cells? Are you looking at residues off the cells? Or, you know, you have to keep these things in mind as far as there's a technology called quantum annealing, and it could do optimization problems at elevated qubits, like 5,000 plus qubits. But it's specific to optimization, and it has, you know, if you look at their website, they said over 250 plus applications. So I would check that out, right? So that's going to get into like kind of that quantum power, but very limited problem set. Quantum annealing, it's called D-Wave. mRNA expression and signal. So on the molecule level, like I say, it's sounding smaller, like you're looking at more things, like more parameters, those types of things. And by chance, I have looked at D-Wave's website, and one of the projects is that. So if you go into it and you talk to D-Wave Systems, is their full name, is you have to be thinking that you're going to be approximating some things. So I know that one of the drug discovery company, they deal with pharmaceuticals, and, you know, they have an agreement like, okay, we just need the specific task done. And then, you know, say the drug discovery company is like, oh, okay, yeah, we can do it with available technology today. It's going to be limited, you know. Yeah, so D-Wave. Yeah, D-Wave is the name of that company. But yeah, you know, any other questions?
Yeah, I had a question. As it relates to your organization, and in particular mental health disorders, like how are you guys applying quantum computing or you know, simulating quantum computation for addressing those issues?
So these are big problems, right? So, you know, and anything, you know, related to the brain, like like how much data are you looking at? So, you know, something basically, if you like were to type down how complex these problems are, it's just you're really dealing with you know, like consciousness and those types of things. So did you have something like a basis as far as like where you're getting, is it like based off a sensor or like a quantum sensor, or?
It's just in general, you know, like what kind of applications can you foresee in your particular organization for addressing mental health issues?
Yeah, so I think it's going to be, you know, they call them killer apps, you know, basically like brain tumors are just like they stick out, dementia, you know, less, and it's more of like a gradual thing. So I'm focusing right now on image analysis, so brain image analysis, and then, you know, pinpointing exactly, because I had high accuracy with the binary classification, which is a simple task, and then taking it to maybe like a multi-class. There's another paper, it's 3D. So to do 3D images, kind of, and it saves some of the resources that you would run into. But yeah, that kind of route as far as that, and then also do interviews as well, continue to do interviews and say, okay, typically the approach is you use quantum if it's just not possible, like by time wise, and many thousands years it would take for classical. And that could be like, training image sets, and it could be like, the files get so large, and we're not there yet as an industry. We're basically having a quantum simulator support the existing convolutional neural net. And yeah, it's basically brain images that would stand out the most, and then looking for either the performance or the efficiency benefits of quantum in moving this forward.
And that's interesting. I was looking at a use case of perhaps simulating the progress of cancer cells. I think that would be an interesting use case, especially if you start looking across populations of individuals with the same type of cancer and maybe the same area. You could do, multiple simulations about how these things will develop over time.
Yeah, right now it's basically parameters, like 40 qubits on a simulator. That's using like an 80 core Xenon processor, and I think with like a terabyte of RAM. So it'll keep going up. I've heard of an experiment going up to like 62. So it just depends on the amount of data coming in to do something that's considered more pure quantum. Now, the caveat with this, or actually the good thing with this, is that if you can have quantum sensors that are delivering quantum data directly into, it's called unparameterized quantum circuits, is you're skipping a step, and that can help things a lot more. There's a paper by Los Alamos National Laboratory that said that, like, shoot for supervised learning, shoot for using quantum data. That's going to be your greatest potential. Now, the thing with medical images is they're classical, and we don't yet have like an exponential amount of quantum data, and it's going to take some time. So I think in the next year or two, it'd be a good idea as far as like staying with medical images that are classical, converting to quantum, getting better classification accuracies. And there's many papers out there that do that. There's at least 2 COVID. There's, these 4 brain papers. There's, so 6, 7, something like that, at least in medical images. So it's a known thing to go after, and it'll just progress as if we start to move into quantum data. That might not be for another year or two. That's what Fermilab's doing, quantum sensing. And it's just, we have an exponential amount of images. And I think that's just a good situation that we're in, because many other types of healthcare and the types of projects that were mentioned here can't quite do that, because pixels are relatively simple. Like a black or grayscale pixel is just 0 to 255 values. And then you have like 512 by 512 of those. So, and then it's just to classify it, using a simple quantum circuit. But yeah, there's lots to look forward to in the future with this, for sure. And the restrictions are definitely hardware, and then maybe not having the most ideal input source for your data coming in. So this other one, spatial transcriptomics. So this is an omics question where imaging is involved along the expression analysis. And again, are these gigapixel images, or are these megapixel or kilobytes, those types of things? So that's kind of where things are. I haven't found too much beyond, say, these 6 or 7 research papers where it's like, you have basically a 200 by 200 image, or a 256 by 256, and then you're working with that. So a lot of that just depends on, the size of the image, your accuracy requirements, and say loss requirements too. And there's other things with that, like quantum sensing and, ghost imaging that's available to send it to quantum computers. But I was listening to a video on YouTube today, and basically it said that, even though we had an FDA approved software as medical device in 2017, it has been slow, to implement AI on a full scale basis. But that was 2017. And, basically when deep learning got big because of hardware, And then we should be coming off that, and then, you know, hopefully going into quantum, you know, after that, especially with simulators too. And then anybody that we haven't heard from and would like to come on, so Antonio or Ahmad, and it's fine, you could share your story, because obviously you're here for some reason to learn about quantum machine learning. And if it's just basically you just code in Python and then you want to be aware of emerging technologies to use in your field as well, that's fine. And you know, me personally, just get on and start running stuff, right? So find notebooks you can run. There was a question about the algorithms. You can actually go onto Qiskit, just search for quantum entanglement and Qiskit, and it's one of those first like 4 links. And then click on a circuit, and it'll send it to your composer, and you can make modifications to the gates, or you could just go ahead and run it. And just go ahead and run it, and then you ran your first quantum circuit and you got results. So it sounds like something that's like, well, I didn't know what I was doing, but that over the course of time, you get all of those results, and you're like, oh, okay, you know, this makes sense. And you know, it's just the thing to do. So in all these things, I would definitely recommend doing some research into gates. So these are single qubit gates, double qubit gates, and triple qubit gates. And you can find this easily on something like IBM Qiskit. And then research what a quantum circuit is, what it does. You know, basically, a lot of times you're embedding data from classical. You're doing things with quantum gates, which are matrices. It's basically manipulating a qubit. And then you're measuring. So that measurement is a classical operation. So every quantum computer simulator and hardware, real quantum computers, they need a classical computer. They can't function on their own. And there's a book called, well, it's done by Worley, and Quantum Computing for Babies. And you can watch it on YouTube even for free. And I think Chris Ferry as well. And it basically says that same exact thing, you know, that it's for a specific problem that it could do a lot faster, especially as hardware emerges. And it kind of gives you an idea of, you know, where quantum, so say this laptop, right? Like if it has CPU, GPU, you know, what kind of QPU will be in the future? Well, there's like 5 or 6 different types of hardware technologies that could possibly fit that bill, you know, especially as more miniaturized and error is less. But it's that kind of stuff, doing certain things classically, certain things quantum, right? It's not like this, it's like quantum's taking over everything. It's more like right now, especially it's assisting classical as things get better. Yeah, any other questions? And then I saw some as far as like some of these programming languages, you know, a little less familiar with Python, or probably it just means Python is the prevalent language. Yes, let's see. And like there's Python could take forever to learn, right? Or forever to master, right? So if you do a bunch of, say, like tutorials based on YouTube, and then you're joining all these chats, and you find your niche, and that could take months too. But basically, you know, that's where you're comfortable doing quantum machine learning or whatever task. And you don't necessarily have to know everything about every single language. But Ron is correct in that. It says Python. So something like Qiskit, that is called Qiskit Python. So it's built on Python. Most people say you don't really need to know Python, meaning that like all the intricacies of it and like every single list and dictionary and tuple and these types of things, it wouldn't hurt. But at the end of the day, you're probably going to be dealing with a block of code like quantum code that's surrounded by classical code. And to get your quantum advantage, you're either going to be changing hyperparameters or updating that block of code, right? But I would say moving forward for anybody, you know, especially getting into QML, is you're going to want to know like single qubit gates, like a identity matrix doesn't do anything, but it's in there sometimes. Hadamard gate, you know, sets up something for CNOT for entanglement, these types of things. And then your CNOT which is a control X. So it's a 2-qubit gate, and then 3-qubit gates to Foley and Fredkin, those types of things. Yeah, so Ron says it would be great to use what I've learned about QCs to enhance all the areas of medical software too. And again, this is a very broad field. And you know, it sounds more like, yeah, he said billing though. So this is like EMR records and billing, those types of things. But feel free to drop your LinkedIn in the chat. And any other last questions? I appreciate everybody coming on. And you know, it's definitely good to see that on the coding side, things have definitely been built up, and you know, people are going to really start to use this in the future. One of my first YouTube videos that I watched on quantum computing is I don't remember who this was, but an experienced gentleman in quantum physics, and he said basically it'll be like a hockey player taking a slap shot when all of a sudden this field just takes off. And I don't know if that's happened yet, but if we have something close to a practical computer, quantum computer by NSF says this year, that'll definitely help things too. And no matter what happens, even, you know, if a quantum computer, significantly less noise and significantly more qubits this year or next year, I believe you're still going to have quantum simulators, especially in healthcare, because they're noise free. They can be run on CPUs or GPUs, those types of things too. Awesome. Yeah, any other last questions? Anybody wants to put in the chat? Appreciate everybody coming on here. And then, you know, any other last tips, you know, to anybody else in the chat here? I think Ron and I, you know, both kind of said, you know, definitely start off with Qiskit, Qiskit, get a free account. If you're good at programming, you can actually transfer that to, you know, your own Jupyter notebook, the IBM ID, basically with that. So awesome. Well, this has been episode 81. This is May 4th, 2023. Appreciate everybody coming on. Good luck with the quantum programming. Start with the circuits, start with the gates, and have a good and productive rest of your week. Thanks, everybody. Take care.